Hi everyone, welcome back to Life with Technologies YouTube channel. I hope you're doing well and thank you so much for watching this episode. So this is another episode of our Huawei Lab simulation series. Remember, in this series we demonstrate to you how to configure and troubleshoot different networking protocols or networking technologies on Huawei routing devices. So if you haven't watched our previous episodes and you are interested to learn or to practice how to configure different technologies, different protocols, and even how to troubleshoot, how to verify different protocols or technologies on Huawei routing devices, kindly check out our previous episodes on this series. And just a kind reminder that if you are watching this episode and you are yet to subscribe to our channel, kindly support us by subscribing to our channel and also stay tuned in for more upcoming videos. So in this episode, we are focusing on how to implement OSPF stub area and the troubleshooting on Huawei routing devices. We know that OSPF supports the concept of areas where we are taking a large network and we are dividing it into smaller areas. So once we've divided our network into smaller areas, it's very easy to control the size of the routing table. It's very easy to troubleshoot because you have now isolated the network into smaller sub-networks that are easy to manage. So apart from just the normal areas, for example, you can see in these topologies, you can have area 0, area 1, area 2, area 3. These can be just the normal areas in a way that they are allowing all the types of LSAs to be propagated in these areas. But again, OSPF also has what we call the special areas. The special areas will be controlling some types of LSA from being propagated into those areas. We know that OSPF works with LSA or the link state advertisements, and the most common types of link state advertisements we can have type 1, type 2, type 3, type 4, type 5, and type 7. So all these different types of LSAs can be propagated across the different areas. But again, sometimes under special requirements, for example, maybe you have a router that cannot handle many types of LSA, you want to reduce the size of the routing table, you don't want them to have the detailed route from other external areas. So you can configure these special types of areas in OSPF. And one of the most common special area is what we call the stub area. So with stub area, you are configuring a router to restrict some specific types of LSAs, and these specific types of LSAs that are restricted from entering a stub area are type 4, type 5, and type 7. So you only allow type 1, type 2, type 3 LSAs. And once you've configured this area as a stub area, you will have reduced the size of the routing table of this router, and you will also avoid carrying unnecessary external routing information into this area. So you've reduced the size of the LSDB, you've reduced the size of the routing table, you've reduced the number of routes that are propagated into this area. So you will be restricting type 4, type 5, and type 7 LSS from entering a stub area. So if you've done this, how do you ensure that now these routers in this stub area can access to the external network? What happens is the ABR, for example, in this setup, we have R1 which is acting as the ABR. So the ABR will inject a default route into the stub area so that whenever we want to access any external networks, we will be using the default route that has been injected from the ABR. So we've restricted type 4, we've restricted type 5, we've restricted type 7 LSA, but we've injected a default route that will be used for all external networks. But we have allowed type 1, type 2, and type 3 LSAs. So this is what we'll be demonstrating in this lab. You can see that in this topology, we have different areas. We have the backbone area, which is area 1. So we have the backbone area, which is area 0. Area 0 is always the backbone area whenever you are doing OSPF area implementation. And then we have area 1. So area 1, you can see that R1 is connecting to R4. So R1 is the ABR, the area border router that is connecting to R4, and they are configured to be in area 1. And then we have area 2. So R2 is the ABR, or the area border router for this area. And we have R5, that is an internal router for area 2. We also have area 3. Area 3, we have R6 connecting to R3. R3, the ABR. R6 will be like the internal router in area 3. But you can see that for us to be able to demonstrate the external routes, the propagation of external routes, we have another extension on R6. So R6 will be the ASBR, the Autonomous System Boundary Router. And this ASBR, it will be connecting to R7. So on R7, we have ISIS running. So we have ISIS configured between R6 and R7, and we will be importing this route from ISIS to OSPF so that we have external route that will be propagated across the other areas. And finally, we will be now configuring area 1 as the stub area. So this one will be our stub area, and we'll be verifying that we don't have those external routes coming in once we've configured the stub area. So one important thing that you need to remember is when you implement stub area or special areas, you need to ensure that you configure all the routers in that area as stub. So in this topology, you can see that R1 is connecting to R4, just two routers. So we need to ensure that we have implemented the stub configuration on R4 and R1 under area 1. And then our peering adjacency will be up, and we'll be able to achieve our objective of restricting the external LSAs from being propagated into area 1. So this is the topology, this is what we'll be implementing, and the configuration will be step by step. First, we need to configure the interface parameters, we need to configure interface IP addresses, and once we've completed the interface IP configurations, we'll go ahead and implement OSPF. So you should be able to learn how to configure interface parameters, how to implement OSPF, how to verify OSPF adjacencies on this router, and then how to implement stub areas. And finally, you also learn how to configure ISIS and how to do route import from ISIS to OSPF. So this is the implementation that we'll be doing. So just a kind reminder again that if you're watching these videos, you've enjoyed our videos and you are yet to subscribe to our channel, kindly hit that subscribe button and support our channel. So let's start our implementation. So this is the topology in ENSP. I need to log into all the routers, and we'll do the configuration step by step. So we start by R1. So on R1, you can see that we have a connection to R2 and a connection to R4. So we'll be doing the interface configuration and also the OSPF configuration straight away. So on this R1, I will undo terminal monitor, just to ensure that we don't have debug messages coming in once we do any configurations. The screen should be clean, the CLI. I need to be in the system view before I do any configurations. Then it's always good practice to give a name. So I will give it a name of R1. So once we've done this, we'll go ahead and do interface configuration. So I'll start with the interface loopback 0. I need to give it an IP address of 1.1.1.1, mask is 32. And then I will go ahead and do the other interface configuration, starting with gig 00. I need to give it an IP address of 20.20.20.0, mask is 31. Finally, we need to configure the interface gig 0/0/1, which will be IP address 10.10.10.0, mask will be 31. So we've completed the interface IP configurations. Next, we need to configure OSPF. How do you configure OSPF? You need to configure an OSPF process, and then you advertise the networks in the respective areas. So we know that on R1, we have two areas. We have area 0, the backbone area, and then we have area 1. So I'll run the command OSPF process 10. It's always good practice to configure the router ID. So I'll configure the router ID of 1.1.1, and the router ID should always be unique in an OSPF domain. So I'll use the loopback IP as the router ID, and it's always the best practice to manually configure the router ID. So once I've done this, I need to specify the areas. So the first one is area 0, and then we can run the network command. So with the network command, you need to specify the network and the wildcard mask. So this one we'll start by the loopback interface. So this one is like 32. So the wildcard mask will be 0.0.0.0, and then the point-to-point connection to R2.0, the wildcard mask will be, this is 254, so it will be .1. Once we've done this, we'll go ahead and do similar implementation for area 1. So area 1, we only have one network, so it will be network 20.20.20.0. It will be 0.0.1. So you can see these are the OSPF configurations. Display these gives you the OSPF configurations. You can also display current configuration OSPF. It will also give you a similar output. So these are the OSPF configuration that you need to apply on R1. We'll go ahead and do the configurations on R2. So on R2, again, undo terminal monitor. And then we need to be in the system view. Once I'm in the system view, I'll start by configuring the system to R2. Now I can go ahead and configure the interface parameters, starting with the loopback interface. So it's interface loopback 0. I'll give it an IP address of 2.2.2.2, mask is 32. Then interface gig 0/0/0. We give it a point-to-point IP address of 10.10.10.1, because remember the other side we configured .0. So the next IP in this subnet is .1. And then we configure the interface towards R3, interface gig 0/0/1, give it an IP address of 10.10.10.2. And then always remember to give descriptions on your interfaces if it's in a live network or a production network, so that it's easy to identify these connections from the interface descriptions. So gig 002, I need to give it an IP address of 30.30.30.0, mask is 31, that is it. We go ahead and do the OSPF configurations again. OSPF process 10, we configure the router ID to be 2.2.2, and then we need to be in area 0. In area 0, we have the network for the interface, for the loopback interface. So the wildcard mask will be the same, 0.0.0.0, the same way we did on R1, and then the point-to-point connection. So we have 10.10.10.0, mask is, the wildcard mask should be .1. And then the other connection to R3. Display these. We've completed the configuration for area 0. We also have area 2. So in area 2, we only have one network. So it's network 30.30.30.0. Wildcard mask will be .1. That is it. We've completed the configuration on R2. Next, we need to do the configuration. This is, are we on the right router? R2, R1, this is R2. So we haven't opened R2. So let me just redo the configurations for R2, and I can just copy the configuration that we've applied on R3 because it's similar. So display current configuration, we've configured them on the wrong router. So you see we have the OSPF configuration. So I'll just copy this, and even the interface configurations. So sometimes when you are doing this implementation, you need to ensure that you are logged into the right router. So I need to just change the system to, let me first quit, undo terminal monitor. then system view, sysname R2. So with R2, I can paste the OSPF configurations and then the interface IP parameters. This I can also copy the same from R3. These are the interface parameters. So I'll copy these and paste on R2. So I can display IP interface brief. These are the IPs parameters configured. We've also implemented OSPF. So we can now shift to R3. On R3, if you've configured a router and you want to reset the configuration, it's very easy. I'll quit and then I'll run the command reset saved configurations. Yes. And I can just reboot the router. I don't want to save the configurations. Yes. So it will reboot and then it will come up with the default configurations. So that one, it will clear the configuration that we've already applied so that we redo the configurations on R3. So again, when you are doing the configuration, always remember that you are logged into the right router, especially in production. Imagine if I was configuring this router and it's in production, I've configured the wrong parameters on R2, which is already carrying traffic, have overridden some maybe interface IPs, so it will be service impacting. So you need to ensure that you are always on the right router or the right device, a firewall, a switch, or even a server. You just ensure and confirm that you are logged into the right device. So sysname R3, let's quickly complete the configurations on R3. Interface loopback 0. Give it an IP address of 3.3.3.3, mask is 32. And then interface parameters for the back-to-back connection. IP address will be 10.10.10.2, mask is 31.3, because the other side is .2. And then interface to R6. Give it an IP address of 40.40.40.0, mask is 31. Then we can quickly complete the OSPF configuration. So similar configuration, OSPF 10. Router ID will be 3.3.3. We start with area 0, which is the one for the loopback connection, and also the point-to-point towards R2. So we need to advertise the network between the two routers. .10.10.2, mask is 0.0.0.1. Then for area 3, so this is area 3, we need to advertise one network, 40.40.40.0, 0.0.0.1 will be the wildcard mask. So if I display these, you see the OSPF configurations on R3. Finally, we'll go ahead and do the implementations for R4, R5, and R6, which will be very simple because we only have one network that we are advertising the back-to-back connection between the two routers and the loopback IPs. So starting with R4, again, undo terminal monitor to avoid distractions. Then sysname is R4. I need to configure the interface IPs, loopback 0. I'll give it an IP address of 4.4.4, mask is 32. And then interface gig 0/0/0, the IP address will be 20.20.20.1, mask is 31. The other side was .0. And then we can go ahead and implement OSPF. So OSPF 10, router ID, this will be 4.4.4, the loopback IP, area 1. Then we advertise the loopback IP and the point-to-point connection. So this one will be 20.20.20.0, mask is .1. So that is it for R4. R5, we need to do similar configurations. Again, we need to undo terminal monitor. Sysname will be R5. interface, we start with the loopback. IP address will be 5.5.5, mask is 32. Then interface gig 00. IP address will be 30.30.30.1. Quit, and then we can complete the OSPF configuration. So OSPF 10, router ID will be 5.5.5. And then we need to be in area 2, network 5.5.5. Wildcat mask will be 0.0.0, 255.255.255.255, and then network 30.30.30.1. This will be .0. So this is /254. So we've completed OSPF configurations on R5. We'll go ahead do similar implementation on R6 and do terminal monitor. Sysname will be R6. Let me move to the left so that we are able to see the topology. I start with the interface configurations. Interface loopback 0. The IP address will be 6.6.6, mask is 32, and the point-to-point IPs, interface gig 0/0/0. IP address will be 40.40.40.0.1, mask is 31. Then interface gig 0/0/1, the IP address will be 50.50.50.0, mask is 31 also. And then we can complete the OSPF configuration. So OSPF 10, router ID will be 6.6.6. And then it's in area 3. We advertise the networks. So we've completed the OSPF configuration on all the routers. And then we can do the verification. So for the verification, we need to check that our OSPF adjacent these are up. Starting with R1, can display OSPF peer brief. You see that we have two adjacent these, one to router 2 and another one to router 4. On R2, we also expect to have the adjacent this up, display OSPF peer brief. You can see that we have three adjacent this, .1, .3, and .5. So this is the good thing about configuring the router ID. You can see that we can easily tell which router is here, because if you see 3.3.3, you know that this is router 3. If you see 5.5.5, you know that this is router 5. And again, on R3, we also expect that we have two adjacent this, display OSPF peer brief. You can see that it's peering to router 2 and router 6. You can also display just OSPF peer so that you can observe other details. So once we verify that our OSPF adjacent these are up, we can now go ahead and verify the LSDBs. So starting with the LSDB of R1. So we know that we have different types of LSA, as I mentioned when I was starting. So we have type 1, type 2, type 3, we have type 4, type 5, we have type 7. In some scenarios, we'll find type 9, type 10, but the most common ones, we have type 1, type 2, type 3, type 4, type 5, type 7, which are the most common that we'll find in an OSPF network. So if I display OSPF LSDB on R1, you can see that in area 0, we have these three types. We have router LSA. So the router LSA, this is the type 1 LSA that will be generated by every router. And then we have the network LSA. So the network LSA is generated by the DR. And then we have the summary network LSA, the type 3 LSA. So the type 3 LSA will be generated by the ABR, and this is what is injecting the inter-area routes. In area 1, you can see we have the similar. We have two routers, so you only get the type 2, type 1 LSA. You have one DR, so you will have only one type 1. I mean type 2 LSA, and then you have these summary network LSA that are generated by the ABR. So you can see that all these have been generated by router 1, which is the ABR for area 1. But you see that we don't have any external LSA because we haven't implemented any route imports between the different protocols, or between this OSPF domain and another external domain. So on R4, if I display the same, of course, display OSPF LSDB, you can see that we have the router LSA type 1, we have the network LSA, which is generated by the DR, and then we have the summary network LSA, which is generated by the ABR. If I display IP routing table, you will see that we have all the routes. So you can see that we have to 6.6.6, 5.5.5. We have all these routes propagated. We have the LSDBs. LSDBs have been populated with all the different types of LSAs. So this one, every area is just a normal area. We haven't done any implementation for the stub area. And one thing that we need to do first is to implement ISIS between these two routers, R6 and R7. And then we'll verify the external LSAs and go ahead and implement the stub implementations. So on R6, so it's ISIS 10. One thing that I need to do is to configure the network entity. So 49.0010.000, I will just use a random network entity. This one I'll give it .6, and then I'll specify the IS level to be level 2, and maybe metric type. If you want to configure the IS name, I'll give it, this is R6. If I display this, you can see these are the basic configuration that we have on this router. Then I'll go ahead and do implementation on R7. But before I go there, I need to activate ISIS on this connection between R6 and R7. So this is interface gig 0/0/1. ISIS enable. This is how you activate ISIS on an interface. ISIS enable 10. That is it. And then we go to R7. So on R7, undo terminal monitor. Then I'll run the sysname R7. Always remember to give the system name or the host name. Then we do the interface configuration the same way we've done on the other routers. Loopback 0, it's IP address 7.7.7. And then I can configure the other point-to-point connection. IP address, this one will be 50.50.50.1, mask start 1. Finally, we can do the ISIS configuration. So it's ISIS 10. Network entity will be 49.0010.007. IS level, we'll give it level 2. And then I can configure the IS name to R7. Finally, we can activate ISIS on the interface. So if I check interface, loopback 0, I use the same command, ISIS enable 10. Then interface gig 0/0/0, I'll do ISIS enable 10. So we've activated ISIS on the interface. I can verify display ISIS peer. You can see that we have an adjacent that is coming up. On R6, we also expect the same, display ISIS peer. Same, we have a peering that has come up. So I can display ISIS routes. You can see that we have some routes that are coming in through ISIS. So the next stage on R6 is we need to be in OSPF 10. And then I will import route ISIS. This is how you do route import from ISIS to SPF, ISIS 10. So I specify the ISIS process. And many times when you are doing the route import, you always have to use a routing policy. so that you control what is imported from one protocol to the other. Don't always do it like this. You need to specify a routing policy that will control which types of route or which routes are imported from ISIS to SPF, and this one will help you sometimes to control loops in the network. So now I expect that I should be having, if I display OSPF LSDB, you find that we now have some external LSAs. So you can see that we have the router network, the summary network type 3, and then we have the AS external LSAs, the AS external LSA that have been advertised from ISIS to SPF. So if I check on any other router, for example, R3, display OSPF LSDB, you find that we have all these types. You can see that in area 0, we also have the summary SBR that has been generated by the router. You see the AS external LSS, they are there for area 3 also. So when we check now on R4, we had the LSTB. This was the LSTB before we did the route import from ISIS to SPF. So when I run the same command, I now expect to also have, you can see that we have summary SBR, and we also have the AS external LSAs. So we have some external LSA that have been propagated to R4. But when you check from the topology, you know that R4 has only one exit. And maybe R4 is a low-end router that has less memory, less processing power. So you can go ahead and implement stub configurations on R4 so that it doesn't receive the detailed external LSS. So what we'll do is we need to configure the stub parameter on R1 and R4. So I need to be in OSPF 10. Then this was area 1, and I just need to run the command stub. So when I run the command stub, it means I am configuring this area as a stub area, and you see the adjacency has gone down because we need to do a similar implementation on the other end. So with this stub command, you are able to configure this area as a stub. So we need to do the same on R4. Display these are the current configurations, and then I will run the command stub. Remember, this is the LSTB that we have before, and even before I do this, if I were to display IP routing table, you wouldn't expect to find any default route. But once we've done that implementations of stub, we will be having a default route for us to be able to reach to all the external networks. So I'll run the command stub. I need to be in area 1 and then run the command stub. So once I do this, it will take some time. If I display OSPF peer brief, you see that we have an adjacency that is up. You can do peer to see more details. You can see that the neighbor has been up for only 12 seconds. Again, display OSPF LSDB. We still have, you see that we've dropped the external LSS. Before we had these external LSS as shown here. But now when you display OSPF LSDB, we only have the 3 types, type 1, type 2, and type 3. We've restricted the external LSS from getting into area 1. And when now we display IP routing table, you will find that we have a default route. This default route has been injected by the ABR. So we have 0.0.0. Whenever we want to reach to any external network, we will be using the default route that has been injected from the ABR, which is R1. So this one proves that we've restricted the number of LSS. We've restricted the external LSS from being propagated into area 1. And now we have a smaller size of the routing table. We've reduced the size of our LSDB. And now if this router has low processing power, low capacity, it should be able to handle, because it will not be getting all these external informations that it was getting before. So this is it, guys. Again, for us to implement this, we need to run the stub command on all the routers in that area. If you forget to run it on one router, you will have routing issues. So you always have to apply the stub command on all the routers in that area. And then we verify that we have the default route using the command display IP routing table. If I display OSPF route, you can see these are the routes that we are getting. But if you display IP routing table, you definitely get a default route that is coming in from the ABR. And this one confirms that our stub configurations are okay. If I display now, maybe I display OSPF here, you can see that checking for the stub, let me display OSPF interface. Verbose. So for this interface, state is BDR, the DR type is broadcast. Do we have the stub parameter? I think there should be a way you should be able to see whether this is a stub area. That is what I'm looking at. Display OSPF, user question mark. OSPF brief. OSPF neighbor. You have the adjacency that is up. I'll find that command and I will share in the comment section so that you can be able to see that OSPF flag, the stub flag that has been set. And even when you capture some packets on these connections, if I start packet capture on this connection and just capture OSPF packets, I only need OSPF. You can see that these are the OSPF packet that we are capturing on this router. OSPF header, these are the information that you get, the OSPF hello packet, the options, and many other parameters that you should be able to interact with whenever you are doing this lab, so that you are familiar with on how these protocols operate. So I hope you've enjoyed this session. I hope you've learned how to implement stub and even the basic configuration for OSPF and the interface parameters. And I hope we've all learned something, and I hope to see you in our next episode. Again, if you've enjoyed this session, just kindly hit that subscribe button and share the video with your connection. Thank you so much, and see you in our next episode. Bye.